Okay, so let me just demonstrate in Excel where I don't have to worry about the whole formula. And I can throw in some data points like -3, -4, maybe a couple -5s and things like that. So here's Excel, -3, -4, -5s, a couple of those, -7s. I'll get in some -16s. Maybe some -17s. Guess I better put a -25 in there if I'm saying that there's some in there. I'm not even trying to act like this is the same picture because this would have like 4 -5s. And then I'm going to hit equals STDEV. There's options here in this is Office 2010 or Office 2013. It says standard deviation from the population. That's assuming that that's an entire population of data, or standard deviation from the sample. I'll do sample, although for all intents and purposes of my discussion, it doesn't really matter. But so let's just say this is a sample of degrees from a certain month. It ends up being 6.6. Why is it that it ends up being positive?
I don't know.
It's like a yardstick next to my mean. So when I look at the flag, I'm thinking, okay, I've got -6 point whatever. There's my standard deviation. I can do a standard deviation this direction, or I can do a standard deviation this direction. Whatever number it is, I can think about how standard deviations are the average distance that the numbers stretch away from the middle. And so I may be a distance of 2 standard deviations and cover all my data, or maybe 3 standard deviations would cover all my data. So here's 2 standard deviations. Here's 3 standard deviations. And I could be going the other way to measure. That would be a negative standard deviation, or -1 standard deviation that way, -2 standard deviations. And look at this, I covered all my data there. This is actually what we typically call the usual between 2 standard deviations, and that's a plus or minus, so within 2 standard deviations. Things that are out here are typically what we call unusual. So these 2 points right here out there, -3 degrees and -4 degrees, they might be my unusual. Still very vague, I know. We got to look at the formula. Okay, so go to page 83, and I'm just going to change the mode here a little bit. And this is the population variance. Look at the way it's calculated. Each time you're finding out how far each number deviates, but while you're doing that, then you're squaring it. So even if there was a negative deviation, like the difference between -25 degrees and whatever our middle is, let's say our middle is, I don't know, -17 degrees, even though that might be a negative distance because we're going this way, it's going to be squared and it's going to make it a positive number. Then you're going to add up all those positive numbers. Then you're going to divide by a number, which is positive because it's just the count of how many numbers were in the set. And then if you want to find the standard deviation, you're just going to square root that thing, so it's still going to be positive. So by the formula, this indicates to us how what we're doing will always, the way we're measuring this will always end up being positive. Look over here. This is a pretty good example. The find all the deviations between the salaries, and these are in thousands of dollars for some business, and then they divide by the number of how many there are, and you get the median. The median price ends up being, because there's 10 numbers here, it ends up being 41.5. So then they take 41 minus 41.5. And that's going to be a negative number, right?
Wait, what did you just do to get that?
I know my sum of all the
Right,
data points
right.
turns out to be
415,
415.
right.
Then I divide by 10 numbers
10,
to find the mean. That's that X bar, right?
Oh, okay.
So you're right now you're imagining the flag. There's my X
Okay.
bar, but for a different set of numbers.
Right.
Now I find each deviation. So from every data point, start with the top, I can take this minus the mean. So minus 41.5. I'm probably being a little
Oh,
I'm probably being a little confusing because
no, I got that.
yeah, but over here we're using the notation for population mean, mu, but when I started this discussion, I'm using sample mean, X bar. So I'm not trying to be so confusing, but I'm using X bar because I was using S, and S is population standard, or sorry, sample standard deviation. So I was being consistent. If I was going to be talking about a population set, I would have been using this, right? Like supposing I have all the data points, then this would have been my notation because they would have been parameters and not statistics. Similarly, this calculation right here would have been the population standard deviation. Would have been a little bit different, right?
Right.
6.5 instead of 6.68. But I can stick with that. It doesn't matter what I stick with. The general idea is still the same. So once you find all those deviations, they may have negatives, right? Excuse me. But all those negatives, if you added them up and tried to find their average, you would have gotten 0. You know, I add up all these deviations, how far each one is away from the flag or away from the middle.
Right.
That adds up to make 0. And then I'm thinking like, man, what the heck? If I divide that by 10 to figure out the deviations, I'm just going to get 0 divided by 10 every time. Every time with every set, every data set. And the reason why it's always going to work out like that is because you're always trying to find out how far they are from the middle of the data, which is the flag of the mean. If you're using the calculated middle, the mean, then they're always going to deviate, if you're talking about the sum of all of them, 0 away, right? Their average is going to be 0 away. So in the formula, knowing that that's the case, we wanted to see out what the average was with this trick. We square each of those deviations before we do anything. So instead of using negative 0.5, I'm going to take negative 5/10 times negative 5/10, which will make it positive 25/100. I'll see if they have a table for that. I wonder if they do. Not on this page, maybe on the next one. There it is. So watch. So then they show what would have happened. You can square each one. You get all these numbers. Now these are all going to be positive. So the sum of the squares, and these are the x squares because they're x data values, the sum of the squares of the deviations is going to be positive. And then you divide by n if you actually had the full set, capital N, if it's the sample set, little n, and you get a number. There's your variance. Then you square root that number. There's back to your same units of measure. Like if the original numbers were dollars, then this would be $3, or in this case $3,000 is each deviation, standard deviation. If it was degrees, now this will be in degrees. These are in square degrees or square dollars or square whatever your units are. I have no idea what they're asking. I haven't even read it. I just wanted to go over that because I wanted you to understand it. Now let's go to their question. So, the variance is the negative square root of the standard deviation. No. The variance is the positive square root of the standard deviation. Sure, that was actually the first thing you told me, right? And I don't care if it's population or sample. The standard deviation and variance can never be negative. That is true. Squared deviations can never be negative. I think I like that, and I think I would stick with that. Just read through the rest to be sure. The standard deviation is a positive square root of the variance. Oh, I take back what I just said. I misread it. The standard deviation is the positive square root of the variance. The other one was backward. This is the correct one. The standard deviation, S, is equals the square root of the variance. Does that make sense?
Yeah, but up top you have it the opposite way.
No, it's not the opposite way. I have it reflected. Look, I'll take what I just wrote right here, reading it carefully. You know, the standard deviation is the positive square root. Put it up here, and then I'll reflect this. Sorry. If I can grab it. I'll just move it over like this. See, that's the same as this statement right here. It's just reflected. What was wrong with this is that it said the variance is, so it said s squared is the positive square root of s. Is that true? If you take the square root of a number, do you get the square of the number?
No.
So that's baloney. The notation gives it away. The notation already says that variance is s squared, standard deviation is s. So if you want to know which way to go with the square root, you square root the variance to get the standard deviation. And then what does the rest of it say? Standard deviation and variance can never be negative. The square deviations can never be negative, right? Because you're squaring them, and even if those deviations themselves are negative, like that negative 0.5, the square of them will not be negative.
Right.
So I won't read D because this is for sure the right answer. Excuse me. Why does it keep doing that? What the? All right, I'm done. I don't know what it's tripping on. That's a